All right, so I'm Eric Cueny, assistant professor in the chemistry department, and I'm going to tell you today about catalysis. So catalysis is important, is an understatement, okay? So catalysis is all about how do we convert one chemical into another. And so an uncatalyzed reaction has a very high energetic barrier to converting one chemical to another, whereas catalysis enables us to bring down that energetic barrier to some chemical transformation. And chemistry has a global impact. And one of my favorite chemical reactions, although I don't do any work in this area, is on ammonia synthesis. So ammonia is used as a fertilizer and is the reason why we can have so many people on our planet. However, it also accounts for something like 1 to 2% of global CO2 production, just because of the energy and the hydrogen that goes into this process. Now, we have a lot of CO2 in our atmosphere for a lot of other reasons. And so one of the things that people have been interested in is, can we capture that CO2 and convert it into something useful? So for example, a fuel like methanol, which could be a transition fuel as we transition to green energy. And so as a postdoc, I worked in a DOE Energy Innovation Hub where we were really focused on a cascade catalytic approach to convert CO2 to methanol. And so our goal was to string together multiple catalysts so that we could convert CO2 into, say, something like formic acid and keep on reducing it all the way to methanol. And really, this strategy is something that we borrow from nature, because this is what biology does to convert CO2 into sugars. It has a multi-enzyme pathway because no one enzyme is specifically designed to take CO2 and turn it into a sugar. So this was kind of our strategy. So now, as an independent researcher, we've been interested in continuing to borrow strategies from biology. So biology doesn't just take enzymes and convert, something from A to B and then float around, find another enzyme, B to C. Biology can also string together enzymes and create a channel for substrates to flow directly from one enzyme to another to really more efficiently produce products. And so the question that I had when I was starting my career was, can we use this same strategy with organometallic complexes, so our catalysts that produce things like methanol from CO2? Unfortunately, we don't do any of that just yet, but we're really interested in this strategy. And so what we're doing is thinking about this strategy with two different metal complexes. So at the center of an enzyme is generally a metal complex, active site of the enzyme. And so we're really interested in my group of understanding how two metal centers can actually transfer reactive intermediates between the two catalyst centers. And so we're interested in this aryl group transfer as one step on our way to thinking about, say, CO2 reduction chemistry. But we've been making structural mimics of this transmetallation intermediate of the partial transfer of an arene ring. And we've got a couple of crystal structures and a first paper out, and hopefully a couple more papers coming out soon about this process. And one of the things we're really interested in is not generating too stable of an intermediate, because we want this to actually undergo full transfer of a substrate from one catalyst to another without having to add extra energy to the system. And so that's what we do in my group. So I will leave it at that. Thank you.